analysis of symmetrical and unsymmetrical sections, thrust line and cable profiles. Okay. So this is a very simple unit. In this unit only one type of problem is asked. Okay, there is only one type of problem. There are not many other types. So just one type of problem we need to understand, and that problem will be asked in the examination. Okay, around 10 to 12 marks that problem will be there. So in that problem you need to calculate the pre-stress. Okay, you need to calculate the pre-stress. Okay, that is the maximum stress and minimum stress. Maximum stress and minimum stress you need to calculate. Okay, and it is to be calculated by using three concepts. First is the stress concept. Okay, first is the stress concept. Second is strength concept. Second is strength concept, and third is load balancing concept. Third is load balancing concept. So all these three concepts they will ask you in a single numerical. Okay, only in a single numerical. All these concepts will be asked to you, and we need to find out this. Okay, so for that, for this purpose, now we will see some assumptions are made before moving to this. These assumptions are also known to you very well. These assumptions we have already made while learning the song. Okay. A transverse plane section of the member will remain plane after the bending also. Within the elastic limit, Hooke's law is applicable to the concrete and steel members, that is stress is directly proportional to strain. Stress in the reinforcement does not change along with the length of the reinforcement. Okay. So along the length of the reinforcement, stress in the reinforcement does not change. What is the meaning of this? Now uh, suppose a steel bar is there. Okay, this is steel bar. Whatever may be the diameter of this bar, 10 mm, 8 mm, 9 mm. Okay, so suppose now this is of Fe415. That is stress in it is 415. So at this point the stress is also 415. At this point it is 415. At this point it is also 415. So along the length, okay, the stress does not change. That is the meaning of this third assumption. First two assumptions are already known to you. So we will move further and we will see that what is the strength concept. Okay, so what is the strength concept? Sorry, first we will take stress concept. What is the stress concept? This is stress concept. So very easy, just pay attention. Okay. So now let us assume a simply supported pre-stressed concrete beam of rectangular section pre-stressed by a tendon provided through its centroidal longitudinal axis. So centroidal longitudinal axis means eccentricity is 0 over here. If you see, it is passing through the centroid. Eccentricity is 0. Eccentric means what? Now suppose if I draw the same diagram. Okay, suppose now same beam is there. These are the supports, simply supported beam. Okay, in this way I am showing the support. Now I will draw the centroidal axis. Suppose this is the centroidal axis of the beam. Okay, centroidal axis means this is called as neutral axis. Centroidal axis is nothing but it is neutral axis. And now here, if you see, the tendon is passing through this point. Okay, passing through the centroidal axis. Now instead of this, now suppose imagine that tendon is passing from here. Okay, and these forces will be like in this way. The forces will be there. This P force. Okay, So this is your P now. So now if you see carefully, this is the tendon profile. The, just 1 minute. Now if you see carefully over here, the tendon is passing through, not passing through the centroid. This is the neutral axis, centroid, and tendon is passing over here. So tendon is passing at some distance. This distance, this is called as eccentricity. And this type of tendon, this is called as eccentric tendon. This is called as eccentric tendon. And this type of tendon which is passing through the centroid, this is called as concentric tendon. This is called as concentric tendon. Okay. So let us for time being, uh, for for time being, we will not see this. We will go through this. Once we understood the concept, then we will apply the same concept to this also. Okay. So now here, now see, a simply supported prestressed concrete beam of rectangular section, prestressed by a tendon provided through its centroidal longitudinal axis. Okay. Let P be the prestressing force. Let P be the prestressing force. Then the compressive stress in concrete is P by A. This is known to you. Compressive stress is P by A. Okay. And due to the external loading, dead load and live load, the bending moment M is produced in the section, and thus the bending stress is M by Z. This is also known to you. So now see, if I show you specifically, okay. So now see, this is a this is our beam. Okay. Uh, these are the supports. It is simply supported beam. Now I will draw the centroidal axis. This is the centroidal axis of the beam. This is also called as what we call this neutral axis. And our tendon is passing over the same axis. So this is the line of action of tendon. Okay. And the force P is applied. So now see here, this is the force P. This is the applied force P. This is your force P. And this beam is having some cross-sectional area. So if I want to calculate the direct stress, the notation for this is sigma 0. Okay, we will use this notation, sigma 0, direct stress. So you know that stress is equal to what? It is load divided by area, okay, area of cross section. So this here sigma 0 becomes, it is P by A. Okay. And this force is the compressive force, hence the stress developed is the compressive stress, and our sign conventions are, if the stress is compressive, if the compressive stress is there, then we will consider it as positive. If the tensile stress is there, if the tensile stress is there, then we will consider it as a negative. So this is the compressive stress, so we will consider this stress as a positive stress. Okay, so I will write below this here, here direct stress which is compressive in nature. Okay, so it is plus P by A. For compressive force we take the sign plus, so it is plus P by A. And if I extend these lines, see, if I extend this, I will draw that diagram of the stress. Now see how this diagram look like of the direct stress diagram. So it will be like this. This is your stress distribution diagram for direct stress. Okay. So here the value is P by A at top, and at bottom also the value is P by A. This diagram is plus this, you can call this as a stress distribution diagram. Okay, so this is your stress distribution diagram. It is for what? It is for direct stress. Okay, this is your stress distribution diagram. Now this is for this applied force P. Okay. In addition to this, you know that beam always carries self weight. Okay, so beam is having some dead load, and if we consider some live load, so suppose now this beam dead load and live load both are acting on the beam. Now suppose if both are, so now suppose these both are acting on the beam. Okay, both are acting on the beam. Now see, due to the dead load, see this is the basic logic, you may know this. Okay, due to the dead load, what will happen? Now this is beam. I will draw the line diagram again. So this is your beam. It is simply supported over here. And now let us consider only dead load first. This is the dead load on the beam. Whatever may be the value. Okay, dead load on the beam. Now what will happen to the beam due to this dead load? What will happen? It will bend. It, this beam will bend in this direction. I will draw this beam will bend in this direction. Okay, so you can see that your compression is at top. So we have already discussed this concept. Compression is at top and tension is at bottom. Okay, so your compression developed which is at the top member, and tension developed at the bottom member. Not members, fibers, bottom fiber. Okay. So due to this dead load, bending moment will get generated. Okay. So what is the bending moment of this dead load? As it is UDL, this bending moment will be WL square by 8. Okay. Let us give this name as M. It is the dead load, so I will named it as MD. Moment due to dead load. Okay, MD you can call it as MDL also. Moment due to dead load. Whenever the moment is there, now the bending stress is getting developed. So if I want to calculate the bending stress, here above we have calculated the direct stress. Okay, here we have calculated the direct stress P by A. But due to the dead load, the beam will bend in this fashion. Compression is at top, tension is at bottom, and the bending moment is WL square by 8 as it is a simply supported beam. So this WL square by 8 is nothing but we have assumed taken one notation for it, MD, moment due to dead load. Whatever may be the value, we are not interested in the value. Okay, right now just understood the concept. So the bending stress is equal to, you know the formula for bending stress, it is M by Z. This is the universal formula, you know that. hmm, M by I F upon Y E by R, from that this formula is derived, M by Z. So bending stress, if I specifically says that bending stress due to dead load, then I should consider the bending moment for dead load. Okay, so it is md by z. Now see here, the topmost fibers are there, the fibers which are above the neutral axis. If you see this diagram, I have already explained you. So the fibers which are above the neutral axis are subjected to compression. So the top fibers are subjected to compression, and the fibers which are below the neutral axis are subjected to tension. So tension is negative. So below neutral axis tension is there, above neutral axis compression is there. So in another word I can say that compression is at top, tension is at bottom. Okay, so compression is at top. So at top it is plus, at bottom it is minus. These are the sign conventions. Okay, don't by heart the sign conventions, just remember this, how we have given those sign conventions. Okay, so at top compression is there, compression we are considering plus, here we have already mentioned, and for tension it is minus. Are you getting this? Okay, bending stress. Now, if you plot the diagram of this, okay, here we have plot the diagram of direct stress. Similarly, if you plot the diagram of this bending stress, then how the diagram will look like? Yeah, so here, see. So at top plus md by z, at bottom minus md by z. So the diagram will be in this fashion. It will be like this. md by z, md by z. At top it is plus, compression is there. At bottom it is minus. I hope now it is clear to you. Okay. So similar thing is with that live load. Okay. Similar thing is there with live load. So if we consider it with live load, okay, now if you consider the live load, just wait a moment. This page is not shifting. Okay. So now for live load, I will explain you here only in this video. Hope now you understood. Okay. So now see for live load. Just now for dead load, we have calculated the diagram. So again I will project this. So here we will draw the diagram, so it will be easy for you to understanding. So first of all I will draw this direct stress diagram. This is our direct stress diagram. It is positive. This is P by A at top, P by A at bottom. This is our direct stress. After that we have drawn the diagram of bending stress due to dead load. So due to dead load, when you say this, then at top it is plus md by z, at bottom it is minus md by z. So this is the diagram. Okay, you will get the diagram in this fashion. So at top it is plus. So for top it is plus. So I have plotted to the right hand side of this line, this vertical line. This vertical line. Plus is there, so I have plotted at right hand side. Minus is there, so we have plotted it at left hand side. So this is minus. This is md by z. This is also md by z. Movement due to dead. Now similarly, if we consider the live load also, okay, then what will be the bending moment due to live load? So bending moment due to live load. It is again same. It will be WL square by 8, simply supported beam. and if UDL is there, live load, then I will call this as ML, movement due to live load. Then what will be the bending stress due to live load? So if we calculate the bending stress due to the live load, then it is ML by Z. Okay, M by Z. M is equal to F into Z. So F is equal to M by Z. This is the formula, ML by Z. Now the similar thing is there. Uh, See this beam. So again, this is the beam. Here is the support given to the beam. Simply supported beam is there. Now what will happen due to the load? Suppose now this load is acting. Now this is your live load, not dead load. So due to the live load also, this beam will bend, and this beam will bend in this fashion. This is the bending of the beam, and at top, at top compression is there, at bottom tension is there. Here if I draw the neutral axis, it will be here somewhere at the center from here. It is not drawn exactly, but you can understand. Okay. So the members above the neutral axis are subjected to compression, members below the neutral axis are subjected to tension. So for compression we take it as positive, for tension the sign is negative. So here if I give the sign, plus is at top, minus is at bottom. Again if I draw the diagram will be same. There is no change in the diagram. Okay. So again if I draw the diagram, at top it is plus, at bottom it is minus. So this is the thing. Okay. So here it is ml by z plus, and this is minus ml by z. So hope you understood this. What are these diagrams? This is the direct stress. This is the direct stress due to this pre-stressing force P. This is the direct stress due to this pre-stressing force P. This is the bending stress due to dead load. MD by Z means dead load. And this is the bending stress due to the live load. Okay. Now if I want to calculate the total stress, total maximum stress, sigma max. Okay, total stress at top. Okay. So if I want to calculate the stress at top, sigma T. So what will be the stress at top? Direct stress P by A, which is always positive. Okay. So instead, I will show you over here where the space is more. See here, sigma T. Okay, so it is P by A. So this is our direct stress. P by A, it is always plus. So this is plus. Then at top we are calculating sigma T means stress at top. So at top, so this is our neutral axis. From here neutral axis is passing. So above the neutral axis area is the top area, below the neutral axis area is the bottom area. Okay, so at top P by A plus MD by Z plus ML by Z. Okay, this is the stress at top. And if I calculate the total stress at bottom, then here it is P by A, which is always plus. Okay, then minus MD by Z, and then minus ML by Z. Okay, so this is the stress at bottom. This is the stress at bottom. So nothing. See, this is plus throughout plus. So this is plus. Here it is plus at top. So this is plus at top. This is plus at bottom. Sorry, top. So this is also plus at top. This P by A is plus at bottom also, but this MD by Z is minus at the bottom. ML by Z is also minus at the bottom. So if you add algebraically add this with sign, you can get the total stress. Okay. So this concept is called as stress concept. This overall concept is called as stress concept. Now we will move further. So here you can see this is what are the diagrams which I have explained you right now. Okay. So here mold, see these things I have explained you already right now. So here see the important thing, direct stress is always compressive, therefore it is always considered as positive. Okay, so our direct stress value P by A, it is always positive because it is always compressive. Next is the bending stress. The bending stress may be positive or negative. The bending stress may be positive or negative. So here you can see the same diagram is there, line diagram. This is the external loading. This may be the dead load or this may be the live load because both the loads are acting vertically downwards. Okay. So if you see in this way, this load is acting. All dead load or live load, whatever may be the load. It may be dead load or it may be live load. So see, initially when load is not applied on this beam, this is your beam and this is the position of neutral axis which is shown over here. But as soon as you apply the load, it may be dead load or live load due to which this beam will bend in this fashion. Okay. And uh, the fibers above the neutral axis are subjected to compression and the fibers below the neutral axis are subjected to tension. So plus sign is at the top and bottom at bottom negative sign is there. So here if you see explanation is given further. So this is top and bottom m by z. At top it is plus m by z and at bottom, so at top this value is plus m by z. If it is dead load then it is md by z and if it is live load then it is ml by z and at bottom it is minus m by z. So if it is dead load then minus md by z. If it is live load then minus ml by z. Okay. So now the next thing is this is all this we have considered for concentric tendon. Okay. Now for the eccentric tendon. So till now whatever we have seen it is for concentric tendon, that is tendon passing through the centroid. Now this is the tendon placed at an eccentricity or we can call this as eccentric tendon placement. So what what we will do if it is not passed to the center. Okay. So again the things are very simple. If it is not passed through the centroid, then eccentricity will get developed. I have already shown you in the diagram how the eccentricity developed. Okay. So eccentricity is getting developed, and if eccentricity is getting developed, there will be the additional stress which is due to eccentricity. See what will happen. All the things will remain same. See here, your force is as it is, stressing force P is applied over here. Okay, so your direct stress will be, so it is written over here. What is your direct stress? It is P by A. It is always plus at top and bottom. We have discussed. Now there is no problem in the direct stress. Now this is the stress due to the dead load or live load. Okay, this is the stress due to the moment means dead load or live load. If dead load is there, then what is the stress at top? At top and bottom, what is the stress? I will not write top and bottom specifically. I will just say here stress due to dead load. So stress due to dead load it is plus or minus md by z. This is due to dead load. Okay. And stress due to live load. What is the stress? It is plus minus ml by z. Okay. This MD is moment due to dead load, ML is moment due to dead load. All these things will remain same. Okay. This is also remain same, this is also remain same. Only this is the additional thing. Only this thing is additional thing. Now we will see from where we got this and why it is minus plus P by Z. Okay. So for that we have to go for separate diagram so that you will understand it better. Okay. So now here this is our beam. It is simply supported. These are the supports. Then neutral axis. We will draw the neutral axis. So this is the neutral axis. Okay. So this is neutral axis. And now tendon is not passing through the neutral axis. It is passing at an eccentricity. Okay. So tendon is placed somewhere here. It is placed somewhere here. This is your tendon. And the pre-stressing force is applied on the tendon over here. This is your the pre-stressing force. P means pre-stressing force. Okay. So P is nothing but this is your pre-stressing force. So now if you extend these lines, I will extend this. First we will draw all the diagrams, or at the last we will draw all the diagrams. So let us see that what is happened due to this eccentricity. What will happen? So now this distance is nothing but your eccentricity. Now see what will happen if you consider this neutral axis. Now initially this P is acting over here. Initially this pre-stressing force was acting over here at the neutral axis. So its eccentricity is 0. But now this pre-stressing force is acting at some distance from the centroidal axis or neutral axis. So this P will cause some moment about this neutral axis. Okay, and that moment is P into E. So this moment M, it is nothing but it is P into E. Now see, this moment is positive moment or negative moment. How we decide that positive moment or negative moment? If your moment is the sagging moment, if your bending moment is sagging, then we always consider it as positive. If our bending moment is fogging, then we consider it as a negative. These are the sign conventions for what? These are the sign conventions for bending moment. Okay. Now see over here. This is the level of our. This is the level of our neutral axis. Now these forces will see. This force will rotate about the neutral axis in this direction. This force also rotate about the neutral axis in this direction. The arrows are not clear. I will draw once again so that you will understand better. See, this force will rotate. This will rotate in this direction. Now, if I rotate this about the neutral axis, and if I rotate this force about the neutral axis, so this is the direction. Okay. So, if you look at the direction carefully, both these forces will try to move the beam in upward direction. So because of this, if you see the bending moment profile of this beam will tends to bend in this direction. This is the direction. Okay. It will try to uplift the beam if you see the direction of both the forces. And now in this case, if you see your tension is at top and compression is at bottom. So we will consider always compression as positive, tension as negative. Okay. So now if I want to calculate the bending stress due to eccentricity, this is again your bending stress because additional bending moment is there. But this bending stress is what? This is due to eccentricity. In previous example, your eccentricity was 0. Now eccentricity is present. So bending stress due to eccentricity. It is again m by z. The basic formula is m by z. So m is nothing but it is p into e divided by z due to eccentricity. Now see, your tension is at top, compression is at bottom. So at top it is minus, at bottom it is plus. At top minus, at bottom it is plus because your tension is now at top and compression is at bottom. Okay, so this is the bending stress due to eccentricity. Now I will write all the stresses. Now bending stress due to dead load. If you see the bending stress due to dead load, then it is md by z. It is plus minus. Similarly, bending stress due to live load. Okay. Similarly, bending stress due to live load. So it will be again plus minus ml by z. Okay. And lastly, your direct stress. Your direct stress is always plus. Direct stress is always plus. It is p by. Okay. Now again, if we plot all the diagrams, okay, so this is the diagram of direct stress. It is at top P by A, it is at top plus, at bottom also it is plus P by A. The next will be, next if I draw this bending stress due to eccentricity. Okay, so the bending stress due to eccentricity at top it is minus, at bottom it is plus. So it is in this way. This will be the diagram. This is PE by Z. Here it is minus, this is plus PE by Z. And again the remaining two diagrams will be the same as we have drawn previously. Okay. So here it is plus, this is minus, this is md by z due to dead load. So this is at top minus, at bottom plus. Here at top plus, at bottom it is minus md by z. And last one, total stress at top, sigma t, total stress at top, it is p by a, which is always plus. Then p by z, which is minus at top, plus md by z plus ml by z, and at bottom it is plus p by a plus pe by z minus md by z minus ml by z. Okay. So this is your final equation of stress concept. By using this concept now we are going to find out what is the value of total stress at top and what is the value of total stress at bottom. Okay. So now further we will move to the PDF. So now here this is what is explained. I hope now you understood the things. If anybody is having any problem, you can ask me. here again it is explained. Who have not understood, I will explain it once again. Pay attention over here. See the sign convention. So eccentric moment m is equal to p into e. Okay, p into e is the moment. It develops hugging bending moment. Okay, p into e is the what is the moment is there? It is hugging bending moment. Why it is hugging bending moment? This is your neutral axis. Just this is your neutral axis. Okay, your tendon is placed below the neutral axis. So here tendon is placed, and now your force is acting here. Here is your force acting. This is your force P. P force. And now if you rotate this force about the neutral axis, so now if I rotate this about neutral axis, then it will rotate like this. This is the direction. It will move in this way. Okay, this is the direction. So due to which your beam will bend. If it tries to uplift the neutral axis. Neutral axis uplift कसा होईल? हा पोर्शन जर वर उचलला गेला तर न्यूट्रल ऍक्सिस कसा होईल? असा होईल ना. So this is the bending profile. Okay. And this is the compression is at bottom. Compression is at bottom and tension is at top. Okay, so at top it is minus, at bottom it is plus. So this is what explained over here. Okay, this is the develops hugging bending moment. So here you can see this is the neutral axis, tension is at top, compression is at bottom, compression plus tension minus. So stress due to eccentricity is equal to minus plus P by Z. Minus at top tension is there, plus sign at bottom compression. Okay, this is how it is explained over here. Now I think numerical may be there. Okay. So this diagram, whatever we have drawn, it is there. If a small problem is there on stress concept, then we will take that problem first, and then okay. So here the numerical is given. So you copy down this numerical, write it down. I will overwrite here. Okay. प्रॉब्लेम प्रत्येकदा लिहितो ते बघा तुम्ही घ्या. Stress a concrete beam. The size is 400 mm by 600 mm. Okay. And the span of the beam is 6 meter. Span of the beam is 6 meter. Okay. So the stressing force is provided at 200 mm. Here it is given 200 mm from soffit of beam. Okay, from soffit. Soffit means bottom. Remember this word, soffit. The meaning of soffit is bottom. Okay. Soffit means bottom. So your stressing force of 960 kilonewton. Here it is the force is given. 960 kilonewton is acting at 200 mm from soffit. Okay. Determine the extreme fiber stress. So this is the important thing. So determine the extreme fiber stresses in the concrete at midspan. Okay. So here what they have asked us, calculate maximum fiber stresses, means total stress at top and total stress at bottom you need to calculate, and this diagram is given to you. You can refer this diagram. Here the load is given as 16 kilonewton per meter. They have not mentioned that this is dead load or live load or anything. Okay, at least see. So we will take this numerical now. Just see these values. Keep in mind these values. 400 by 600, 6 meter span, 960 kilonewton is the distressing force, and 16 kilonewton per meter. So we will draw the diagram first. This is the given beam. On this beam, a load is acting. It is of 16 kilonewton per meter. Okay. This load is 16 kilonewton per meter. Then the span of beam is 6 meter. Span of beam is 6 meter. If nothing is mentioned, consider the beam as a simply supported beam. And if in the problem the condition is given, if any other support is there, then take that support accordingly. So this is the simply supported beam now. Okay. So now we will draw the neutral axis. This is the neutral axis of the beam. And now we will draw the tendon profile, tendon line, and this is the tendon line. Okay. And the pressing force is applied to this tendon somewhere here. So along this tendon the pressing force is applied, and the value of this force, it is how much it is, 960 kilonewton. Okay, 960 kilonewton. And the cross section of the given beam, it is very much 400 mm by 600 mm. And they have given us this this tendon is at a 200 mm distance from the soffit of the beam. Okay. Now see, the section is of 400 mm by 600 mm. So 400 mm is the width and 600 mm is the depth. So this total distance is 600 mm depth. Okay. So out of 600, this is the neutral axis. Neutral axis passing through the centroid of the beam. So if this total is 600, then this will be 300. So I will mark the distances. See, this total, this total distance is how much it is? This total is 600. This is 600. Now what is the distance from neutral axis? So this distance will be 300 mm. So if this is 300 mm, This total also 300 mm. Okay, so I will take this line a little away so that you will not get confused. Okay, so this bottom distance from neutral axis to this bottom, this is also 300. So out of this 300, again I will mark over here this total is 300, and out of this, from soffit, from here, the distance is given as 200 mm, and this is given in the problem. Okay. So finally, our eccentricity will be, this is our eccentricity E, and it is E is equal to how much? This 300 minus 200, so it is 100 mm. This is the eccentricity. And what they have asked us, they asked us to calculate sigma top, that is sigma T notation, stress at top, and sigma bottom, that is sigma B. This we need to calculate. Okay. So now first thing is, it should be clear in your mind that the tendon is not at the neutral axis. So tendon is not placed at the neutral axis. So eccentricity is not zero. Eccentricity is present, and if the eccentricity is present, bending stress due to eccentricity is also present. So problem is very simple. We will go step by step. So first of all, eccentricity is equal to, it is 300 minus 200, which is equal to 100 mm. This is eccentricity. Then calculate the direct stress. Okay. So calculate the direct stress. So direct stress. This is equal to, what we can say, direct stress is equal to P by A, load upon area. So P is given as, this is P by A, and this is always positive. So it is, P is 960 pre-stressing force. P means pre-stressing force. And 2 times to 3 divided by 400 into 600. Okay. So direct stress. What is the value? Let me know the value of this. Let me know the answer, because then every time I have to minimize this, go to the PDF and then see the answer. Instead of that, do the calculation and let me know the answer fast. 4. Okay. So it is 4 Newton per mm square. 4 MPa I will write. It is 4 Newton per mm square. So this is the direct stress. After that, for bending stress, we need to know the value of section modulus. Section modulus Z. What is the section modulus? It is always I by Y. Okay. Now what is I? I is the moment of inertia. Okay. I is the moment of inertia. So which moment of inertia you are going to take over here? Ixx or Iyy or Izz? Which moment of inertia we are going to take over here? We will take Ixx, okay, divided by Y. Why it is Ixx? Because if you see, this is your beam, this is the neutral axis of the beam, and this is your beam. When beam will bend, this bend along the x-axis. This will bend along the x-axis. This neutral axis will bend like this. It will bend along the x-axis. So the section modulus is, it is Ixx by y. It is always bent along the x-axis. So now I by y means what? It is the rectangular section. What is ix for rectangular section? It is bd cubed by 12. This is the ix divided by y. Y means what? Y is the distance of extreme fiber from the neutral axis. So on the either side. Okay. So y, this is the distance. This is your neutral axis. Okay. So from this neutral axis up to this point, this is the extreme fiber. This is nothing but this distance is y. You can call this as yb, distance of bottommost fiber. And similarly, you can say that this distance from neutral axis to topmost fiber, this is the distance, and this is we called it as yt. This we called it as yt. So here bd cube by 12 ix and y is whatever may be this total d. This is your d. So y will be d by 2. So if you simplify this, then it is bd square by 6. Then it will become bd square by 6. So simple is that. So just put the values, you will get the value of section modulus. So this is equal to your V is 400, D is 600 square divided by 400 into 600. From this we will get the value of Z, 24 into 10 raised to 6. Okay, 24 into 10 raised to 6. What is the unit? So Ix is in mm raised to 4, Y is in mm, so this unit is mm cube. Unit is mm cube. So this is the value of your Z. This is the value of Z. Okay. So now after the calculation of Z, now we will calculate the moment due to eccentricity. Moment, or directly we will calculate the stress. Instead of increasing the steps now, I will directly calculate a bending stress due to eccentricity. So it is PE by Z. Okay. So PE by Z. Later on we will see minus plus. So P is 960 into 10 to the power 3 kilonewton per Newton into E is the eccentricity, it is 100 mm, whole divided by Z, 24 into 10 raised to 6. Find out the answer. 1 Newton per mm square. This is the sign convention. So 4 Newton per mm square means what? It is 4 megapascal. Either you can write in megapascal or in Newton per mm square. Plus minus, you know that the bending stress due to eccentricity at top, tension is there, at bottom compression is there. Okay, so it is minus plus. It is at top it is minus, at bottom it is plus. Okay, minus plus is there. So now, if you see the numerical in the B here, they have directly given you this load of 16 kilonewton. They have not given you the separate load of dead load and live load. Okay, they have not given you, or it is not mentioned in the problem that this 16 kilonewton is whether it is live load or dead load, and the cross section dimensions of the beam is also given. So from the cross section dimensions we can calculate the dead load of the beam. Okay, and we will assume that this given load is the live load of the beam. Okay, so now moving further here, right, in the examination also you should write like this if it is not given, as dead load and live load are not specifically mentioned. Therefore, assume assume live load is equal to 16 kilonewton per meter. Okay, this is your live load. So now, if you this is your live load, then bending moment due to live load, calculate this ml. Okay, bending moment due to live load. So the beam is simply supported beam carrying UDL. So it is bending moment due to live load. It is WL square by 8, which is equal to W is 16. Span is 6 divided by 8. Calculate this value. And let me 72, but it is in kilonewton meter. Remember this. It is in kilonewton meter. Now calculate the bending stress due to live load. Bending stress due to live load, which is equal to plus minus ml by z, which is equal to plus minus ml is 72 kilonewton meter, so 72 into 10 raised to 6 divided by z. Z was 24 into 10 raised to 6. So it is plus minus 3 megapascal or Newton per mm square. This is the bending stress due to live load. Now finally we will calculate what is remaining now. Direct stress calculate झाला, bending eccentricity मुळे येणारा bending stress calculate झाला, live load चा bending stress झाला. आता dead load राहिला. Okay, so first dead load calculation. Okay, so dead load DL is equal to, so the dimension of beam is 400 mm by 600 mm, so it will be 0.4 into 0.6. Assume that it is per meter, so into 1 per meter and into 25 density of concrete. So what is the answer? Kilonewton per meter is our dead load. Okay. So now calculate the bending moment due to dead load. Bending moment due to dead load. This is MD, bending moment due to dead load. It is again simply supported beam carrying UDL WL square by 8. That is 6 into 6 square, that is span, divided by 8. It is 27 kilonewton. So bending stress due to dead load, it is MD by Z. It is 27 into 10 raised to 6 divided by Z. 24 into 10 raised to 6. What is the answer? 1.125. This is plus minus 1.125 kilonewton meter. Sorry, unit MPa, Newton per mm square. MPa, Newton per mm square. Okay. So now we will calculate the total stresses, or we will call this as a resultant stress. So the resultant stresses resultant stresses. So the first stress at top, stress at top, that is sigma T, which is equal to, it is P by A, which is always plus, minus P E by Z plus M D by Z due to dead load plus M L by Z due to live load. So sigma T is equal to P by A. What was the value of P by A? P by A. P by A is 4. P by Z is minus 4. So P by A is plus 4. P by Z is minus 4. Then MD by Z. MD by Z is 1.125 plus ML by Z minus 3. ML by Z plus minus 3. Okay. So plus 3. So sigma T is equal to, this 4 will get cancelled. 3 plus 1 4. It is 4.125 MPa or Newton per mm. This is your total stress at top. Similarly, calculate the total stress at bottom. Okay. So total stress at bottom. Second, stress at bottom or soffit. This is sigma b. It is P by A, direct stress, which is always positive, plus PE by Z minus MD by Z plus ML by Z. Sigma B is equal to P by A, it is plus 4, again PE by Z plus 4 minus 1.125 minus 3. So therefore sigma B is equal to, what is the value? Okay, so it is 3.875 Newton per mm square or mm. So now the final thing is problem not end here. You need to draw the diagram also. That is the end of the problem. So while drawing the diagram now, extend your neutral axis so that we can use same neutral axis to plot everything. So this is the neutral axis. Okay. Now I will extend these lines so that we can draw a diagram. So now first thing is that this is our given beam, loading is there on the beam, okay, and tendon, where is the tendon located? It is located below the neutral axis, somewhere here it is located. How much is the eccentricity we have calculated? This is the eccentricity and it is E is equal to 100 mm, and your stressing force is acting somewhere here, and the value of the force 960 kilonewton. Value of the force is 960 kilonewton on both the sides. So first we will draw the direct stress diagram. So this is the direct stress diagram. At top and at bottom it is positive, plus, always positive. So at top it is plus 4 Newton per mm square, At bottom it is also plus 4 Newton per mm. Then P by Z diagram. So P by Z, it is at top minus 4 and at bottom plus 4. So if minus sign is there, plot it to the left hand side, and plus is there, plot it to the right hand side. So this is minus 4 and here it is plus 4. This is the diagram. Minus and plus, minus 4 at top, plus 4 at bottom. Now next is MD by Z diagram. So this diagram may be like this. At top it is plus and at bottom it is minus. So at top it is plus, at bottom it is minus. And the value is 1.125 MPa. Here it is minus 1.125 MPa. Okay. And next, live load. This diagram will be similar to dead load diagram. Same direction. Unless there is change in the value. Diagram is same. So here it is plus 3 plus, here it is minus 3 Newton per mm square. All these are the stresses. And now we will draw the final diagram after doing all these things. What is the stress at bottom? 3.875. And what is the stress at top? 4.125. So first of all, diagram. So this is your baseline. Okay. So the value of your sigma top, sigma t, it is 4.125 Newton per mm square, and sigma b bottom, it is 3.875 Newton per mm square, that is MPa. So now at top it is 4.125 and it is positive. Both the values are positive. This is also positive, this is also positive. We haven't get the negative answer. So positive means here up to this point. And I will write here 4.125 Newton per mm square. Then 3.875. So this is 3.875 up to this point. By taking the judgment, you can draw this 3.875 Newton per mm square. And when you join these 2 points, this is your resultant stress diagram. This is sigma T, total stress at top. This is sigma B, total stress at bottom. And this is your resultant stress distribution diagram. Okay. I hope now this problem is clear with you. If anybody is having any difficulty, you can ask me right now. Just see the all the steps of the numerical. If you are having any difficulty, then let me know. Just one moment. So this is the stress concept. Whatever we have done right now, this is nothing but the stress concept. So I will give you 1 minute. Please go through all the steps of the numerical, and if anything is not understood to you, then let me know right now, because only one example I am going to take for one type. I will not take the second example of this type. So please go through the steps and let me know within 1 minute if you are having any doubt, any difficulty. So now this is also a very simple concept. So here in the load balancing concept, you are going to use two formulas. Okay, two formulas. One is for the bent tendon. Bent tendon means the tendon which is showing over here. This type of tendon is called as bent tendon. Okay, if you see the profile of this tendon, it is, see, this is the profile of this tendon, like this. This type of bar is used. Okay, this is the profile. This type of tendon it's called as bent tendon. Now see this distance. This is nothing but your eccentricity E. This is nothing but your eccentricity E. Here the eccentricity is not constant. If you see this distance is different, this is different, this is different. So we consider the maximum distance, maximum eccentricity. Now this is a beam. Again this is the pre-stressing force as usual. Pre-stress is applied over here. So this is the pre-stressing force, and this is the bent tendon. Suppose it is bent and at an angle theta. Suppose now this angle, whatever this angle is there, this is theta. And if this angle is theta, then this will also become theta because these two are the alternate angles. Same is the case with this one. This will be also theta. Okay. See now. How do I calculate? What is the value of tan of theta? How do I calculate the value of tan of theta? Okay. Now, if I want to calculate the value of tan of theta, you see over here. This is our, consider this triangle. Consider this triangle. Now, if we draw this triangle separately, then it will look like this. This is the triangle. This is your angle theta. Here is the angle theta. This is your eccentricity E. And if, now see, if this total length is L from this point to end point, if this total length is L, then this length is by default it is L by 2 because it is always bent at the center. So this length is L by 2. Now see, if you use tan of theta over here, tan theta, what is the formula? It is opposite side divided by adjacent side. So what is your opposite side? Opposite side is E. This is 90 degrees, so this will become your hypotenuse. This is your hypotenuse, so your adjacent side is L by. So tan of theta is E divided by L by 2. Here it is given. Tan of theta is E divided by L by 2. So as theta is very small, theta tends to 0, sin theta is nearly equal to tan theta. It is very true. You can check it on the calculator also. Take a very small value of theta, that is theta is equal to 0.02 or 0.04, like these values. Then you will find that if you do it on the calculator right now, then you will find that the sine of the same angle is equal to tan of the same angle. When theta tends to 0, that is theta is nearly equal to 0. Okay. So therefore it is sin theta is equal to tan theta. So I can write over here sin theta is equal to E divided by L by 2. Okay. So now here if you see, the concept is explained over here. What is exactly happening in this load balancing concept? See now, this is your eccentricity. This is angle theta. This distance is L by 2. Okay. If this force is P, if this pre-stressing force is P which is acting over here, then in the tendon P force is getting to be developed. Okay, if the applied force is P, then in tendon also the force will get generated is P. And to maintain the equilibrium, this force in the tendon will be in opposite to this force which is externally applied. So now if I say over here that this is the P, this is the P force which is in the tendon. This P force, it is get generated in the tendon. Okay, this P force. If you don't understand, then here I will draw the separate diagram. See, this is our horizontal line. Instead of drawing the horizontal line, I will directly draw the bent tendon. So now this is the tendon line, and now here the force is okay. So now pre-stressing force P. So the pre-stressing force P, it is over here. This is the acting pre-stressing force P. So P is the force. But this is the externally applied force over here. इथं हा force externally applied केलेला आहे. But due to this externally applied force P, here in the tendon the same force P is getting developed, and that force is equal and opposite in nature of the external force. Okay, and now you know that this angle is already theta. So if you project this, if this angle is theta, if this angle is theta, and if you resolve this force here, if you resolve this force, this P which is in the tendon, then what you will get? So you will get one line parallel to x-axis, another line parallel to y-axis. Okay, now if you draw the arrows on these lines, so this is the arrow. So here this will become P cos theta. Okay, this will become P cos theta, and this will become P sin theta. Similarly, at this end also, at this end also, here the angle is theta. Again, if you resolve the force which is on this side, this side also the a part of the tendon is there, that is P. Okay, so if you resolve it again, then one component parallel to x-axis, another component again parallel to y-axis. Okay, so here this is these two components. So this will be again P cos theta, horizontal component, and this will become P sin theta. So P cos theta and P sin theta, P cos theta are equal and opposite forces. So these two forces will get cancelled. See here, this P cos theta and this P cos theta will get cancelled. And here P sin theta plus P sin theta. So the total upward force you are getting over here, see here, this is the total upward force which you are getting, and this force it is 2p sin theta. And the 2p sin theta इथून आलेला आहे. Okay, so the total upward force which is which is shown over here, this is the total upward force due to the provision of bent tendon. It is 2p sin theta. म्हणजे याचा अर्थ काय की जेव्हा जेव्हा तुम्ही बीम मध्ये हॉरिझॉन्टल सरळ टेंडन प्रोव्हाइड करायच्या ऐवजी असं बेंड टेंडन प्रोव्हाइड केलेलं असतंय, तर त्यावेळेला ह्या टेंडन कडून एक रेझिस्टिंग फोर्स मिळतो बीमला अपवर्ड डायरेक्शन मध्ये, and that force is nothing but it is 2p sin theta. This is the force. Okay, so we will quickly go through the theory of this. Some pointers are there below. The pre-stressing force in the tendon is resolved into the two components, P sin theta and P cos theta. Just now we have seen that. P cos theta is acting equal and opposite to each other, so it will get cancelled. P sin theta, both are acting along vertical upward directions, as we have seen that both the P sin thetas are acting vertically upwards. Hence the sum of the two components is 2p sin theta. So their sum is 2p sin theta. Okay. Now see, already here what is mentioned. See here. Now already here is the force of. Now already here is the upward force of 2p sin theta. Okay. Why this force is getting developed? Due to this provision of this bend tendon. If you provide the bend tendon, then this 2p sin theta force is generated. Now on this member, suppose now a vertically downward force is acting. Okay. Suppose now vertical downward force W is acting. W. Then what will be the net force? Net force काय असणार आहे इथं? Then W is the downward force acting minus upward force is 2p sin theta. This will be your net force. 2p sin theta. Why it is 2p sin theta? Because of this bent profile. This is not a horizontal tendon. This is the bent tendon. Okay. So here that point is mentioned over here. So if W is the downward load acting on the beam, then the net effective force can be determined as W minus 2p sin theta. Okay. So this 2p sin theta is point load. So this W must be a point load. Then and only then this formula is valid. For UDL, different formula is there. Okay. For UDL, different formula is there. So it is W minus 2p sin theta. Okay. So this is for the point load and for bend tendon profile. So today it is sufficient. We will stop over here.